Welcome to yet another video where we're doing dot product for linear algebra or maths 1503. Okay, so the dot product basically measures how closely two vectors point in the same direction, and I have three scenarios to kind of make you understand what I mean. Scenario number one would be if two people are pushing a car in the exact same direction. So if one person is pushing this way, say the square is a car, right? And another person, actually, this doesn't make sense. So if this is a car and they are pushing this way, okay, don't know if I'm making sense, and another person is pushing this way. So if two people are pushing a car in the exact same direction, the car would obviously move easily, and thus the dot product is large and positive. So because all of them are going this way, that means the car would obviously push in that direction, and the dot product would be positive and large. Secondly, if one person is pushing north, so another person is pushing, let's say it's this car, so this person is pushing north, and another one is pushing east. Where is east? I think this is east. So another person is pushing east. They're pushing at 90 degrees, obviously, and none of them is helping the other one, and hence the dot product would be 0. So if you think of it, let me just try to have little dotted lines. If you could see here, they're pushing at exactly 90 degrees, and thus no one is helping one another, so the dot product would definitely be 0. Or third scenario would be if one person is pushing forward, so I forgot to draw a car, so another person is pushing forward, and then another one is pushing backwards, like that. They work against each other, and hence the dot product would be negative, right? So one is pushing in this direction, another one in that direction, the dot product would obviously be negative. And this basically tells us that the dot product basically results in a constant and not a vector. So it just depends on what the people are doing, and whatever results we get from that would be a constant or a number, a value, and not a vector. Before calculating the dot product, vectors should be or should have the same number of components. Here I made some examples. So as you can see, this time you have 2 and 3, 5 and 7. This is our 2 or vectors in 2 dimension, and therefore they can be dotted. However, if you have 2, 3, so this is our 2, and 5, 7, 9, that's our 3, or a vector in 3 dimension, and therefore they cannot be dotted. So if you're dealing with 2-dimensional vectors, or a plane, vectors in 2-dimensional planes, you have to obviously dot those two. But if you have different kinds of planes, you can't dot them. So if it's 3-dimensional, it has to stick to 3-dimensional. I have here a little formula that I kind of want us to work on. So if U is this 2-dimensional plane vector, meaning you have a Cartesian plane with only X and Y, and what's this? V is also that. If you're calculating the dot product, you basically want to go like this. So you'd have U1 times V1, and then you add U2 times V2, right? So you would have U1 V1 plus U2 V2. And it does make sense, because if I had a 3-dimensional, let's say with V, what would I basically be multiplying it with, right? So it wouldn't make sense. So that's why if you're dealing with 2-dimensional, you have to only have 2. And if you have 3-dimensional, you have to work with 3-dimensional. Kind of wanted to say something, but I forgot. Oh, I wanted to say, actually, as you can see here, one would argue, why am I starting with U when I'm like doing my multiplications instead of V? Because here I'm starting with V dotted with U. With multiplication, or with dot product, actually, once we do the properties, I just need for you to now remember that they can be commutative. So it's fine. You can do the reverse. Like in this case, you could have had maybe this part, and then for this one, you could have V2 and U2. Right? So it wouldn't matter as long as it's dot product. But once we do the cross product is never commutative. So just remember that for now. I have a little, oh, actually, I want us to also try this one with 3D. So if you have U with U1, U2, U3, and V with V1, V2, V3, once you do the dot product, you basically want to multiply U1 with V1, and then you add the multiplication of U2, V2, and then you add the multiplication of U3, V3. And this is a symbol for dot products. Once we do the cross product, you'd see the difference. So cross product would basically have a cross like that. So V is crossed with U. This time V is dotted with U. So you basically have, let's just do v1 multiplied by u1 plus v2 u2 plus v3 and vu3 actually. And as you can see, this is going to give you a constant, right? So this is going to give you a multiplication, basically gives you a constant, and then you add that constant to another constant, and then you add that constant to another constant. That means you basically have a constant as your result, right? So dot product always returns to us a constant, not another vector. Let's try this example where we have this vector being dotted with this vector, and I'm saying dotted because I see this big dot. It's not multiplication, because if it was multiplication, you wouldn't even have a multiplication like that because it's gonna maybe confuse you. Instead, they would have a vector here in brackets and then another vector in brackets, right? So just know your multiplications. And also, if you're doing vectors, you wouldn't really have two vectors being multiplied to each other. Instead, you would want to say either dot products or cross products. And then if things are being multiplied, they would really just give you a scalar multiplied to a vector. So dot product of this would be 1 times 2 plus 2 times -1 and plus 3 times 5. This is going to give you 2 minus 2 plus 15, which is really just 15. Can you see that that's basically a constant or just a value? And this tells us maybe that this the dot product of this is positive and maybe also large. Dot product can also be written as this. So this is another formula for dot product. If obviously, because we only just learned this one, so maybe u1, v1. I'm just gonna do the r2 and u2, u3. Oh, v2, sorry. Right, so for now we only just know of this, but dot product, obviously if you have angles you can work it out like this, and this is basically derived from, if you do remember your metric or your grade 11, where in trigonometry you were doing the cosine rule. If obviously you want to calculate cosine theta and you don't have a 90-degree triangle, you would use the cosine rule, and it's basically derived from that, right? So this is another formula if you have maybe your magnitudes and an angle between those vectors. So this basically tells us that the dot product is dependent on, number one, the first vector, so vector u, and sorry, the length of the first vector, and then times the length of the second vector and the angle between them, right? So right, because if you remember correctly, when I was doing the third or the second scenario where you had 90-degree, another person pushing north and then another one pushing east, there's an angle. So dot product is also dependent on an angle. And this formula, right, this second formula that I showed you, it can be manipulated as this. So remember what dot product is. So if you have u, or the vector u, dotted with the vector v, like this, okay, let's rewrite so the magnitude of u, magnitude of v, and cos theta. For this side, you know what dot product. So if you're not given the overall answer of your dot product, you can just let's say we have r2, you would have u1 v1 plus v2 u2, which is equal to the magnitude or the length of the first vector multiplied by the magnitude or the length of the second vector and the cosine angle between the two vectors. So it can be manipulated like this. It just depends on what's given to you and what you can make out of what's given to you. Also, this formula, we mainly use this, let's say this formula or the first one, if they want you to find the angle between the two vectors. Yeah, most of the time that's the case. Let's talk about the orthogonal or perpendicular vectors. I just want to also add in another name for this, could be normal. So they could say the normal or orthogonal, or it could be perpendicular. So two vectors are orthogonal, perpendicular, or normal if they meet at right angle, right? And if they do meet at right angle, remember the third scenario, that would mean the dot product between the two is 0 because they basically working against each other, right? An example of this would be, let's say you're given this vector 2, 1, dotted with 1 and -2. The dot product between the two would be 2. times 1 plus 1 times negative 2, and that's 2 minus 2, which is 0. And because our answer is 0, that tells us that these vectors are orthogonal or perpendicular or normal, and that's because they work against each other. Let's talk about the properties of dot products. If vectors are commutative, or the dot product is basically commutative, you have something like this. So you either have maybe u dotted with v, and this is equal to v dotted with u. Right? So it's equal. You can try examples to check out, and the answer to this would be a constant, or the result of this would be a constant, and the result of that too would be a constant. Okay, well, vectors can also be distributive, where if you have the vector u dotted with the vectors v plus w, this is equal to u dotted with v plus u dotted with w, right? Okay, let's talk about what the results would look like. So looking at the distributive, if you have this here, this a vector plus another vector would give you a vector. And if you dot product this vector plus this resultant vector that you got here, it would give you a constant. And this is why it's equal to this, because if you have a vector dotted with another vector, it gives you a constant plus another constant. That is overall a constant. And then for associative would basically mean if you have maybe vector u plus vector v plus vector w, this is equal to vector u plus v, or the vector v, and plus the vector of w. Let's talk about what this would give you. So with associative, if you have two vectors being added together, the resultant would be another vector. And if you add that vector that you just got to another vector, you basically get a vector, right? And then if you, on this side, if you have two vectors added together, you get a vector plus another vector would give you a vector. So for associative, or in this case, you have a vector as your resultant. Let's talk about the scalar. So this basically means if you have c scalar with the vector u and dotted with v, this side you would get, let's say, c, and then you have u, or the vector u dotted with w. Okay, let's talk about what the resultant of the two would give you. So if you have a scalar, c is a constant, multiplied to another vector would give you a vector as your resultant. And if you dot this vector with another vector, you're getting a constant, right? And remember your BODMAS, so every time you just want to start with the bracket instead of the outside. So here you have the vector u dotted with the vector w, it would give you a constant. If you multiply a constant with another constant, you obviously get a bigger constant, and that would be, or results in, a constant. And then let's talk about the self dot product. This is important for if obviously you doing cross products as well. You would want to know the self dot product because yeah, there's a whole proof going on in the cross product that revolves around whatever I'm going to tell you now. So if you have vector u dotted with u, this is basically equal to the magnitude of the vector u squared. Right? Because let's try to kind of analyze this first, and then we're going to see. So we know that this is going to give us a scalar because u times u is a scalar. However, I just want us to also dot the two and see, right? So you would have u1 multiplied by u1 plus, let's just do vectors in two-dimensional planes. So u2 and u2, right? So this, you could just write it as u1 squared, right, plus the u2 squared, right? Hope I'm not losing anyone. And this basically would give you a constant because you're adding this constant to another constant, and you would result to a constant. Let's try to prove why it's equal to the magnitude squared. So if obviously you have a vector u, the magnitude of that would be u1 squared. Oopsie, I think I have the subscripts in the wrong place. So u1 squared plus u2 squared, and this basically says we have to square the magnitude. So if we square that, remember what happens, the square root is going to cancel this square, and you'd basically just be left with u1 squared plus u2 squared, right? And this is why they're equal, and that's because the final answer is the same. So if you're given two vectors that are the same and are being dotted, just know that its magnitude is just this. So you don't even have to have the square roots, just have u1 squared plus u2 squared, and that's the magnitude. That's it for the video. Next time we're going to be doing the cross product, and then we move on to complex numbers of linear algebra. And I think that would be it for the series. I'm not sure if I should add the things like your determinants, your inverses, like the transposes and stuff like that. I'm not sure. But yeah, that's it for the video and of dot product.